Okay. So, octet rule. All atoms except hydrogen and helium want 8 electrons in their outer shell. That's pretty much the whole reason for chemical bonding. Those electrons that are involved in a bond, do you remember what they're called? You should. You should. What do I call those electrons that are involved in chemical bonding? Or which part of the atom holds the electrons that are involved in chemical bonding? What do we call that outer shell? It's another name for it. What? Valence. So we find them in the valence shell. They're called valence electrons. And they're the ones found in the outer energy level, or the outermost shell. You can say it any of those ways. There was a guy named Lewis, and he came up with a simple way to show valence electrons, and kind of like a way to keep track of them. So we have something called a Lewis symbol, which can also be called, it depends on where you look, a Lewis dot structure. The structure, though, lots of times has to deal with like a whole chemical compound, not just one element. It will give the element by symbol, and then it shows outer electrons by dots. So pull out your periodic tables if you don't have them out. Am I writing too little, Lily? I'll make it bigger. Okay, so I want you to find nitrogen. Clay Gump, what group's nitrogen in? Group 15 or 5A. More? Oh yeah, I didn't move enough, did I? So what does that tell me? How many electrons does nitrogen have in its outer shell? 5. So by looking at the group, it tells me 5. So when I do this, I put my element symbol in the center, and then it's super simple, and then I just add dots. 1, 2, 3, 4, 5. The way you put the dots on is arbitrary. Put 4 around and then put your 5th one in. I've done it enough that I know like sometimes where I'm going and where I need to put the electrons so I can show them moving well. But there's no right or wrong way to do it as long as you have the correct number of dots around the chemical symbol. So, does this particular atom that I chose obey the octet rule? Does it have an octet in its outer shell? No. So I should be able to look at this, if I'm just given this, and I should be able to hypothesize about what this atom wants to do, which are things that we already know. We know it wants an octet, and we know it has 5. So I know that it needs to gain how many electrons? 3 electrons. So you can look at those kind of things and you can tell. Now basically we keep using this word octet. There's something called the octet rule that comes into play in this chapter, and it says atoms tend to gain, share, or lose electrons until they get a full outer shell. And by this we mean 8 electrons, or an octet. If I have an octet of electrons, what 2 sublevels are full? What's wrong, Connor? You don't know? Grace, don't. So if I have an octet, what sublevels are full? Thank you, Grace. S and P are full. Who doesn't want an octet? Thank you. Okay. Now, that's a nice rule. There are some exceptions to it. Of course, every rule, you know, seems to have some exceptions. Can you guess what part of the periodic table doesn't follow the rule well? Where are those guys that might have multiple ionic forms? Like iron and tin and all of them. Where do they fall on the periodic table, Jacob? Yep. Transition metals. They always have to be a pain. It works great for the S's and the P's on the blocks on the periodic table. The D block doesn't cooperate so well. They usually lose from their D and you don't end up with an octet. You might have 5 or 6. But then when they overlap with the S level from another energy level, they manage to get 8, but it's just not pretty. In the transition metals, you have to look at the elements. Individually to see what they do. So we're going to take this idea of octet and the octet rule, and we're going to apply it to the different types of bonds that the atoms like to form. So we're going to start by talking about ionic bonding. Let's see. Hey Lydia, can you tell me what things like to bond to form an ionic bond? Like what's the first part compared to the second part?
Metal and metal.
Okay, so this is a metal. Plus a nonmetal. And remember, these guys, my nonmetals, are not noble gases. Anything else is fair game. When you see the equations for these, for the formation of an ionic bond. They look kind of weird. And I'm going to use something easy. I'm going to use sodium chloride. When we write these, we are thinking only about 1 unit of the end product. So the equation looks kind of weird. We know sodium exists monotomically. It's a solid. We know chlorine gas on Earth exists like this. And on the other side of the equation, I know I'm going to get sodium chloride in solid form. The only time that you guys in this class, now maybe if you go further in chemistry you'll see it again, but the only time you're going to see something weird like this is when we're talking about ionic bond formation. Rather than balancing this and having 2 NaCl's out here, we want to look at 1 unit at a time. So I come in, and this is the only time it happens, I put a 1/2 in front of there. Normally we don't ever use fractions in balancing an equation. The other thing that you'll see most of the time with these is delta H. It's like that, and that stands for heat of formation. Now remember, when these guys hook up, they're happier because they have full outer shells. So that means that energy is given off in bond formation when we're talking about ionic bonds. If it's given off, is it exo or endothermic? Good. So this is exothermic. And when I show the heat of formation, I'm going to write this. I'll let you get this, and then I'm going to write it over on the next page. So I've got a clean equation. We good? So let me write that. It's going to look like this. Na solid plus 1/2 Cl2 gas yields NaCl solid. Delta heat of formation equals negative 410.9 kilojoules per mole. I just wrote it over bigger because it was kind of squishy. When I look at this, I can say that Na, if you're asked to evaluate it, lost an electron. Cl gained an electron. So from here to here, there's electron transfer. Now, when I look at this and when I think about it, I should be able to link this to the last chapter. So let's take a second and do that. If I look at Na versus Cl in terms of ionization energy, what kind of ionization energy does sodium have based on the trend and where it is on your periodic table? What, Chloe? Yeah, good. So this has a low IE. What's chlorine have, Marissa? Good. So this one has a high IE. So it makes sense that when I look at this pair, sodium would be the happier of the two to give one up. It also makes sense if I look at my periodic table and I see sodium has 1, chlorine has 7. And this is what we see, or what I would call typical ionic compound formation. So now let's look at that and see what it looks like as a Lewis structure, or a Lewis dot structure equation. I'm just going to write Lewis structure. If you have a different colored pen or pencil, grab it, because it's kind of nice when you go back to look at this stuff to be able to when we write the Lewis dot structure, we don't worry about the fact that on Earth chlorine has to be a gas and we need 2 of them, because we just want to look at 1 mole of the substance. So I will write my Na plus Cl and my arrow, and now I have to go in and I have to actually show my electrons. So put your electrons around sodium, 1, and then put your electrons around chlorine. So when I start, that's what it looks like in terms of electrons. Does that make sense to everybody? Then on the other side of the equation, what happens to sodium's electron? It gives it to chlorine, right? So I just show sodium in its ionic form, plus, when I have the atom that gets the full outer shell, I show it in brackets. And then I place the electrons around it. And I show its negative charge outside the bracket. So sometimes you'll be asked about this arrow and what it indicates. First of all, it indicates transfer of electrons. It also indicates, if it's an ionic compound, I would say that now each ion has an octet. And over here, this bracket just indicates that it now has all 8 electrons. So now, try lithium iodide. Am I right? I almost forgot to put my sign. Don't forget your sign. All right, I'm going to make you try one more. If I can move the paper. Calcium oxide. Does yours look like mine? We good? So this is pretty simple. And that's what they're always going to look like when you deal with ionic compounds. And because of the way these electrons interact and the ions form, it gives ionic compounds specific properties. So we're going to find that covalent versus ionic have very different properties, and we're going to use them in lab. I was hoping for Thursday, but I think notes are going to take us one day longer than I thought. So these specific properties tell us a lot about ionic compounds. Ionic compounds are brittle, solids. They have high melting points. They are what we call crystalline. In structure. Okay, so four big ones. Brittle solids, high melting points, crystalline in form, and the crystals exhibit something called cleavage, which means if I hit them just right with a hammer or a chisel or whatever the tool is that I use, they'll do something called cleave, and that means they break into individual crystals, like right along a plane, and you can see it very clearly. I'll pull out some things tomorrow, some minerals, just so you can see what the cleavage looks like. We don't really do anything with it in here, but it's just something you should have an idea in your head what it looks like. So all of these things result from electrostatic forces. And those are from the electrons. The electrostatic forces are what are responsible for, basically they keep the ions in a rigid, that's why they're brittle, well-defined, so it's pretty easy to see, three-dimensional arrangement. Have you ever looked at a piece of salt when you shake it out of the shaker? If you haven't, you should. Shake some in, have you never looked at it, really? No? Look at it tonight. Go home and shake some in your hand and check it out. And see if it doesn't have a very clear and easy to see crystalline structure. Because it does. We'll go just a little bit longer and then I'll stop. Energies of ionic or ion bond formation. Sometimes it's called energetics. I don't like that word. So let's use our example we used before when I gave you NaCl. NaCl was a very exothermic, and you'll find most of these are because they're becoming more stable when they form a bond. So it makes sense that they would give that energy off to the surroundings. And I think we had negative 410.9 kilojoules per mole of energy that was given off. The loss of an electron from an atom is always exothermic. And we have to think about it when it's gained, so it doesn't just get lost. It's gained by another electron, or by another atom, I should say, sorry. And that's when we have to start thinking about endothermic. So we'll kind of break that down a little bit. So when we look at this, we're going to look at our Na, and we're going to look at our Cl. So when Na goes to Na plus, we've lost an electron, but it's going to be picked up somewhere. So I'm looking at here 496 kilojoules per mole. Chlorine becomes Cl minus. It's gain an electron. And it gains negative 349 kilojoules per mole. Now, do those balance out perfectly? No, they don't, and they won't when you look up the numbers, and that's okay. That means something's given off to the surroundings. When I want to find the energy requirements or find the energetics, I have to look at the total process. When I look at the total process, I have 496 kilojoules per mole plus negative 349 kilojoules per mole. Get your calculator out, do that math. Uh-oh, I need batteries. When I add those together, I can look for a positive or a negative sign, and that just tells me if the process is endo or exothermic overall. I think that's a good place to stop. Now I'm going to have to go through the stuff that's on that blue paper and tell you what you can and cannot do based on how far we got today.